Hey guys, welcome back. Today we are starting our discussion of chemical equilibrium. We're going to spend a couple of lessons on chemical equilibrium, and then we're going to be using it after that to talk about acids and bases. So kind of a mini unit, you could say. All right, so chemical equilibrium. Basically, we're talking about reversible reactions. So here's an example of a reversible reaction. So anytime you see that arrow going in both directions, you know that the reaction is reversible. So once you form the products, those products can go back to reactants. Um, and that doesn't work for all reactions. So reactions that are not reversible would include ones where precipitate forms, because essentially once you form that precipitate, that insoluble solid, it is essentially it takes those products and sort of clumps them together so that they're not available to react, to split apart and give you the reactants again. So the precipitate forming sort of sequesters those products in one place and doesn't allow them to react anymore. You can also have a reaction not be reversible if a gas forms and then escapes. So, if you have some hydrogen bubbles being given off and they're going into the atmosphere, well, you're not going to get the reaction to go back in reverse. Um, and then if the products are a lot more stable than the reactants, so like a combustion reaction is not going to be reversible because, the CO2 and H2O that form are so much more stable, so much lower on that potential energy diagram than the reactants were, that they're not going to be able to get back up over that activation energy hill to go back in the other direction. So if a reaction is reversible, it will eventually, if left alone, and we'll talk about what happens when we're not leaving it alone, but if it's left alone, it's going to reach what's called chemical equilibrium. The word equilibrium in general just means a balance between two opposite processes. So two opposite things happening at the same rate. So it could be, migration from place to place, like across state lines, happening at the same rate. And if that's true, then your populations are going to remain relatively constant. Your bank account could be at equilibrium. It could be unchanging for a couple of months because you're spending at the same rate that you're earning. So equilibrium just means a balance between two opposite processes. Chemical equilibrium specifically refers, of course, to those two processes being forward and reverse reactions. So the example in the CK12 passage, and you can see I brought in the picture of the little people that they had colliding with each other, and I'll talk about that in a second. Um, and this was from the TED Ed video. If you didn't watch that, definitely go back and watch it. I thought it was pretty good. But if you have H2 and I2 coming together to make 2HI, um, what's going to happen is at first, only the forward reaction can happen. So the forward reaction starts out way up here at a very high reaction rate. And the reverse reaction would be at zero because at first, all you have are the H2 and the I2. You haven't formed any HI yet, so the reverse reaction can't happen. But as soon as you start to form some HI, then the reverse reaction can start to happen, and so you can see it speeding up, right? So it even shows you here the reverse reaction would be 2HI goes to H2 plus I2. Eventually, they reach an equilibrium state where both reactions, forward and reverse, are happening at the same rate. Um, in the case of the little analogy from the video, you have normal people bumping into each other on the street, and an arm is transferred from one person's body to the other person's face. Okay, uh, kind of a goofy example, but it kind of works because if you think about these guys over here in blue as your reactants, your left side of the equation. When you begin, the only thing that can happen is the formation of these, like, arm-faced people and armless people, because there are no armless and arm-faced people at the beginning to bump into each other and reform the normal people. Um, so the equilibrium state would be where rates become constant and also equal to each other. So hopefully you can look at the graph and see that the rate of the forward reaction and the rate of the reverse reaction are the same and that they are not changing. Okay. Now that does not mean that concentration, remember the brackets mean concentration of, that does not mean that the concentrations are the same. So if you look at these numbers up here, let's assume that this is at equilibrium in this example. You have 907 pairs of, your normal people, and then you have 93 pairs of, face arm, face, whatever. But you have a lot fewer of your products. Okay, just because the rate of the formation of the arm face people and the regular people, the two, whatever you want to call it, just because the formation is the same in both directions, doesn't mean the populations are the same. So that is the difference here. We're not talking, if we're talking about concentration, our graphs might look something more like this. So here's the same reaction. So HI being your product would have started down here at 0. And I don't quite know why this line doesn't start all the way down at 0. It kind of looks like the graph got shifted over a bit. But anyway, the HI would start at 0, and it would increase very rapidly because the only thing that's happening at first is the forward reaction. And the reactants would decrease very rapidly because the only thing, they're getting used up at first. But eventually, once you form more and more of your product, your HI, that allows those HIs to then react and reform your H2 and I2, which is why their concentration is only dropping steeply at first. And then over time, as you're reforming and getting the reverse reaction going more and more, it stops dropping so sharply and levels off. And the same thing for the HI. At first, it's going up very dramatically, very drastically. And then as you're using some of it up, well, that's going to keep it from rising as quickly. And so you can see it's rising less and less quickly, and eventually it levels off as well. So when these two lines are parallel to each other, we would say the reaction is at equilibrium. Okay. The same thing over here. This is the exact same thing. The same reaction, everything. I'm sorry. This is the reverse reaction. So now we're using HI as your reactant. So if you started with only HI in the vessel to begin with, then what you would have would be a different situation because now HI is your reactant, so it starts very high. Notice in either case, though, the HI at equilibrium has a much higher concentration than the H2 and the I2. Whether you start with H2 and I2 in your reaction vessel, in your flask or whatever, or if you start with the HI in that flask, they will eventually reach equilibrium. And notice your concentration of HI compared to H2 and I2 are very, very similar. We top off HI very high in terms of concentration, H2 and I2 very low in both cases, no matter how we started. And the reason for that is because for each reaction, we have something called an equilibrium constant expression, or KEQ, which tells us at equilibrium which substance or which side of the reaction, reactants or products, will be favored. So if you look at just sort of the general equation or example here, these little lowercase letters are the coefficients, and the uppercase letters are the substances. The way you write a KEQ expression or an equilibrium constant expression is it's simply KEQ is equal to the concentration of products over reactants. So therefore, if we said something like, okay, if KEQ is greater than 1, which one do you have more of at equilibrium, products or reactants? Right. So in any fraction, if your answer is going to be greater than 1, that means you have more of the numerator. So you're going to have more products, right? So if I write sort of a generic KEQ expression for this example, we would say KEQ equals, and then my two products get multiplied by each other, but also raised to the power of their coefficients. And you should have seen that in the reading. But my first product is C, so I'm going to say concentration of C raised to the power of its coefficient, which is just symbolized here by a lowercase c. You can see that there. Okay, so I just put it there. And then times the concentration of D raised to the power of its coefficient. Okay, and then on the bottom I have my reactants, so it would be A to its coefficient times B to the power of its coefficient. So that is an equilibrium constant expression. And we will be next time plugging in some numbers and actually doing some calculations with this. So if we take a look at one more, going back to the reaction we just did, what would the KEQ expression look like for this one? Okay, so you should have said that KEQ for this one would be concentration of HI raised to the second power, because its coefficient right there is 2, that's my product, over concentration of H2 times concentration of I2, both to the first power because their coefficient is 1. Notice too, we're only able to express concentrations, which means if we can only express concentrations, what are the only physical states that we're going to include in an equilibrium constant expression? Right, so you should have said aqueous or gases, right? Because you can't really have a concentration of a solid or a liquid. Those are pure, okay? So if an equilibrium, and I do need to go back and talk a little bit about this word favored. You'll hear that a lot. Favored just means which one is in greater concentration once we reach equilibrium. Because if you go back to our graph here, they're not going to be equal, right? I mean, you've got your HI way up here and your H2 and your I2 way down there, and that's actually the case for both graphs. So if I look at my KEQ expression with HI to the second over H2 times I2, okay, so there's my KEQ expression. What do you think based on our graph, and I'll zoom out a little bit so you can kind of see both at the same time, based on our graph, there we go, do you think our KEQ would be greater than 1, equal to 1, less than 1? What do you think? Okay, so you definitely should have said that for this reaction, KEQ would be greater than 1. And of course, the reason for that is my numerator, HI, is up here. It's higher in concentration. So whatever the number that is here that goes in for the concentration of HI is going to be bigger than these two numbers down here. So hopefully that makes a little bit of sense. And that means what? It means that reactants are favored or products are favored. Right. So it means that products are favored at equilibrium. Now the last thing I'll say about KEQ is that it does depend on temperature. We'll talk more about that later. But this graph might look a little different, and the answer that you would get by plugging in real, experimental data for concentrations of all three of these substances, the answer that you get for KEQ would be a little bit different at a different temperature. So, for example, this might be at room temperature. I don't know. It might be at 25 degrees Celsius, but maybe at 50 degrees Celsius, you might have these two lines a little bit closer to each other, or they might be further apart. It just depends on the reaction. But we'll talk a little bit more about that later on.